Hi, everyone. So I'll be presenting on behalf of Dr. Frank Voest today. I'm Bryce, and I'm a PhD student in the Frank Voest Lab in the Department of Oncology at the U of A. So today I'm going to present on our development of a novel lanthanum-133-135 theranostic pair. Some results I'll present were highlighted in a scientific reports publication and a recently published article in the Journal of Nuclear Medicine. So before I jump into our research, I'd like to review some key techniques. So positron emission tomography, or PET imaging, is a functional diagnostic imaging technique using radio tracers to visualize in vivo processes with high sensitivity and specificity. So the image on the right shows a patient scanned with fluorine-18 FDG, revealing liver metastasis of a colorectal tumor due to the tumor's elevated sugar uptake. Now, when diagnostic and therapeutic radionuclides are paired together, this is termed theranostics. Preferably isotopes of the same element, these radionuclides are labeled to the same molecular targeting vector for concurrent diagnostics and therapy. So the image below shows how particle-emitting radionuclides can be employed for therapy, while photon-emitting radionuclides can be applied for diagnosis, with both radionuclides attached to the same targeting vector. To illustrate the concept of radionuclide theranostics, this patient depicted had advanced metastatic prostate cancer and failed 9 different treatments, including chemotherapies, immunotherapies, and radiotherapies. When administered several doses of actinium-225 PSMA, consisting of an alpha particle emitting actinium-225 radionuclide coupled to a prostate-specific membrane antigen targeting vector, the patient exhibited a complete response. These diagnostic PET imaging scans were obtained using gallium-68 PSMA, which uses the photon emissions from positron decay of gallium-68 to visualize the patient's tumor burden. So this shows the immense potential of theranostics, precise therapy with a therapeutic radionuclide that can be tracked with a diagnostic radionuclide using the same targeting vector. Now, one challenge with gallium-68 diagnostic imaging of actinium-225 is that gallium has different chemistry than actinium, and its 68-minute half-life is much shorter than the 10-day half-life of actinium-225. So to improve the accuracy and capabilities of imaging the biodistribution of actinium-225 radiopharmaceuticals, it's highly desirable to have a PET radiometal with a longer half-life and similar chemistry to actinium. So with theranostics in mind, our objectives were to demonstrate high-yield cyclotron production, purification, and radiolabeling of a novel lanthanum-133-135 theranostic pair. So lanthanum-133 is a positron emitter and is well positioned for diagnostic PET imaging with actinium-225 owing to their chemical similarity. And lanthanum-135 is an Auger electron emitter, which is our therapeutic surrogate for actinium-225. These Auger electrons have a lower energy than alpha particle emissions, giving them potential with the right targeting vector to also be highly cytotoxic to tumor cells. So in this presentation, I'm going to focus on the applications of lanthanum-133 for PET imaging. Lanthanum-133 is a potential surrogate for lanthanum-135 or highly potent actinium-225 due to their chemical similarity. It has an attractive 3.9-hour half-life, which simplifies preparation and distribution. Its positron energy is quite low, suggesting a high PET imaging spatial resolution, and its associated gamma rays are low energy and intensity, simplifying handling and reducing patient dose. Finally, it has excellent chelation chemistry with common chelators, which bodes well for radiopharmaceutical application. So to expand on what I discussed on the previous slide, lanthanum-133 compares quite favorably to other commonly used PET radionuclides with respect to its fundamental properties. Lanthanum-133 has a lower maximum positron energy of 1 MeV compared to gallium-68, scandium-44, and lanthanum-132, which suggests a higher PET imaging spatial resolution. Lanthanum-133 also has lower energy and abundance co-emitted gamma rays compared to scandium-44 and gallium-68, which significantly reduces radioactive dose to patients. Finally, although lanthanum-133 has a lower positron branching ratio of 7% compared to other common PET radionuclides, copper-64 and zirconium-89 also have low positron branching ratios, and these two isotopes have produced many excellent PET images. So we didn't see the low positron branching ratio as a major impediment for PET imaging. So how do we make lanthanum-133? First, we needed to develop novel cyclotron targetry to encapsulate the sensitive barium target material. What we developed is an indium aluminum target assembly, which sandwiches the barium pellet between an aluminum target disc held together by indium wire. This target design is fast to assemble, easy to handle, it's storable, you can reuse it, and it can be adapted to produce other radiometals. So to produce lanthanum-133, 135, we need to select an appropriate cyclotron beam energy. As you can see, the red reactions produce lanthanum-133, the black, lanthanum-135, and the blue, lanthanum-132. We want to maximize lanthanum-132 production and maximize lanthanum-133 production and minimize lanthanum-132 production, which we viewed as an impurity due to its high energy positrons. So we bombard our target at 22 MeV to maximize lanthanum-133 production and minimize lanthanum-132 production. Now I'd like to highlight how the isotopic abundance of barium impacts radiolanthanum production. It's easy to make lanthanum-135 due to the high abundance of barium isotopes that permit its production. However, for positron-emitting lanthanum-132 and 133, lanthanum-132 has a significantly lower abundance of barium isotopes for its production compared to lanthanum-133. So our perspective changes significantly if we weight the nuclear cross-sections for this isotopic abundance. As you can see from these isotopic abundance weighted cross-sections, producing lanthanum-133 is far easier than producing lanthanum-132 across all beam energies. This has important implications for scale-up to clinically relevant PET imaging activities. So we irradiated the targets at 22 MeV on our TR24 cyclotron to produce lanthanum-133 and 135, and at 11.9 MeV to produce lanthanum-132, 135 as a comparative theranostic pair. And as you can see, the yields of lanthanum-133 are far higher than lanthanum-132. This permits production of clinically relevant PET activities with a short cyclotron irradiation. Looking at one of our higher energy runs at 22 MeV, after irradiation, there's a significant amount of short-lived lanthanum-134 and 136 at end of bombardment, as well as small amounts of lanthanum-131 and 132. However, after several hours, these short-lived impurities have decayed significantly, leaving large activities of lanthanum-133 and 135 for application. To separate barium and lanthanum, we used a lead-shielded Neptune mosaic LC synthesis unit and modified the separation outlined by the angle group. So after irradiation, we download the sealed target assembly, peel back the aluminum cover, and dissolve the barium target material in high-purity water. Separation is performed using branched DGA resin and varying concentrations of nitric acid to load lanthanum on the column, then wash away the barium target material along with other metallic impurities. Finally, we elute the lanthanum with 0.1 molar HCl, which is ready for radiolabeling with minimal metallic impurities. Now, this was a good start. However, there's still more room for improvement. So as shown earlier, although it's much easier to produce lanthanum-133 than lanthanum-132 via the barium-135p3n and barium-134p2n reactions, we can still improve this yield. So we pursued cyclotron production of lanthanum-133 using barium-135 carbonate target material, isotopically enriched to 92.7%. Adjusting the cross-sections for this enriched isotopic abundance, we get two distinct reactions. Irradiating at a lower energy of 11.9 MeV allows high yield production of lanthanum-135 via the barium-135p-n reaction, while irradiating at higher energies allows significant production of lanthanum-133 via the barium-135p3n reaction. To maximize lanthanum-133 production with enriched barium carbonate target material, we performed our high energy irradiations, extracting our beam at 24 MeV with a target incident energy of 23.3 MeV. And we also again performed irradiations at 11.9 MeV to investigate yields of lower energy lanthanum-135 production. For 23.3 MeV runs, we install our target with the aluminum cover facing forwards. And for 11.9 MeV runs, we flip the target around and install it in reverse. with the aluminum target disc acting as a built-in degrader to lower the cyclotron beam energy. The lanthanum-133 yield from the enriched barium-135 are significantly higher than using natural barium carbonate. And at lower energies, we can make large activities of lanthanum-135. So this gives us the flexibility to produce either large amounts of lanthanum-135 for Auger therapy or lanthanum-133 for PET imaging. Since we're using very expensive isotopically enriched barium-135 carbonate, we designed a recovery process to recover as much of it as possible. For this, we saved the first 30 milliliters of processed solution coming off of the resin, which we determined contains all the barium carbonate. We then neutralized the solution with ammonium hydroxide and then added oxalic acid. This results in the rapid formation of a white precipitate, barium oxalate. We then collect the precipitate and heat it in an annealing furnace to convert the barium oxalate to barium carbonate. We then quantified the recovery of dried barium carbonate and determined it was over 95%. So after the separation is complete, we use 100 microliter aliquots of our highly pure lanthanum-133 to radiolabel the chelators DOTA and MACROPA. So to radiolabel these chelators, we first adjust to pH 4.5 with sodium acetate buffer. Then we react at 90 degrees Celsius for 30 minutes with DOTA and room temperature for 10 minutes with MACROPA. We achieved full incorporation and 130 gigabecquerels per micromole with DOTA and 206 gigabecquerels per micromole with MACROPA. Now, beyond our production of lanthanum-133, our group recently performed some phantom and preclinical PET imaging on our Invion PET-CT scanner. So first, we investigated the PET imaging spatial resolution of different PET radionuclides with a mouse-sized Derenzo phantom assembly, which contains rods of varying diameters that are filled with the radionuclide of interest. And there is a strong correlation between the radionuclide positron energy and its spatial resolution in the phantom. Lanthanum-133 clearly exhibits superior spatial resolution to scandium-44, the widely used radiometal gallium-68, and another radiolanthanum PET candidate, lanthanum-132. So this highlights the excellent image quality obtainable from lanthanum-133. And finally, we radiolabeled PSMA-INT with lanthanum-133 to test preclinical PET imaging in Allen-Kapp prostate cancer tumor-bearing mice. Our labeling procedure achieved a molar activity of 73 gigabecquerels per micromole. As you can see in the left image, the Allen-Kapp tumor is clearly visualized with high spatial resolution in the mouse. Next, for a blocking experiment, we used the PSMA targeting agent DCF pill. And as you can see in this image, mice pre-dosed with DCF pill exhibited significant tumor blocking of lanthanum-133 PSMA-INT. So to conclude, we demonstrated highly scalable cyclotron production of lanthanum-133 using novel cyclotron targetry that simplified production and post-irradiation handling. We explored the fundamental PET imaging characteristics of lanthanum-133, with phantom imaging highlighting the favorable PET imaging spatial resolution compared to scandium-44, gallium-68, and lanthanum-132. And we achieved the first in vivo preclinical PET imaging of lanthanum-133 in Allen-Kapp tumor-bearing mice. So taken together, this suggests that lanthanum-133 is a strong radiometal candidate to provide high-resolution PET imaging alongside actinium-225 alpha particle therapy or alongside lanthanum-135 Auger electron therapy. Finally, I'd like to thank the members of the Frank Wust Lab and others at the University of Alberta and Alberta Health Services who were involved in our project. And thank you for listening. I'd be happy to take any questions.
Thanks, Bryce, for the interesting talk. We do have one question from the audience, from Francisco Pesina. He's asking, how do you compare the overall performance and costs of lanthanum isotopes with the standard FDG for PET applications?
Yeah, so I think that there's a lot of factors there. It has to do with what tracer you're using, as well as the activities. FDG is very well established for PET imaging, but the problem with FDG is that it has a relatively, fluorine-18 has a relatively short half-life of 110 minutes. So it really limits what you can do in the body. So what we're looking at with lanthanum is using it with a longer half-life and a chemistry that's similar to actinium for these long-lived applications in the body, such as with antibodies and longer-lived pharmaceuticals. So I think that there's also just a fundamental difference between what you can achieve with FDG versus other targeting vectors with radiometals.
Thanks. I don't see any other questions, but I could maybe have time for one quick question from my side. I was wondering, did you explore at all the radio stability of your chelator complexes with this new novel lanthanum isotopes?
Yeah, so we haven't done things like EDTA challenges yet. However, we did just test them in reaction solution after 48 hours, and they were still fully incorporated by radio TLC. So the lanthanum was stable in both the DOTA and macroPA chelators after extended periods of time.
Thanks. All right, great. And I think in this case, then we can move on to our next speaker.